Okay, so here's our first example of just a diagram. We're not even going to throw any numbers at this whatsoever, right? To me, for what we're covering in here, what becomes a little bit more important is that you understand what I'm calling the dynamics, right? Which is all of the forces that are enacted here and what the result of that is with a picture, okay? Because I think this is something that we can all sort of relate to. So in the tug of war model below, two teams are pulling the rope in different directions with different forces. What direction does the red ribbon travel in as the teams are pulling? So one thing I mentioned in the previous slide is the length of the vector describes the magnitude of the force. It determines how, for lack of a better word, how hard they're pulling, right? So when you see this, team one's rope is pulling in this direction. That's not, again, that's not the length of the rope, okay? That is how hard they're pulling in that direction. Team two's rope, this is how hard they're pulling. This is the force they're applying in that direction. So what happens is this object, this flag that I've drawn as in red here let's keep it red, yeah, shall we? Okay. This flag right here is going to move based on the forces that are being enacted upon it. And the resultant force of this object and the way that it's going to move is determined by these two magnitudes. So if we have this team pulling in this direction and we want to know the resultant force, the simplest way to express this is to say the resultant force is equal to, I'm going to call this rope 1, okay, plus rope 2. I add these two forces together. I don't subtract one from the other. I add them together because they are both being enacted upon this object. So if I add these two ropes together, where does this flag, what's the force that it's moving with in what direction? And we talked about how to do this a while ago. Some of you have seen this, okay? When we want to add one vector to another, we take this and we move the initial point of this vector, we literally copy and paste, to the terminal point of that vector, okay? And the resultant vector is connected from here, which was the initial point of R1. We connect that to the terminal point here. So in other words, this flag, the green vector that I've drawn in here, represents the force of this flag moving in this direction. Okay, and if you're wondering, like, does it matter if I do that? Whoops, let me get rid of that. Does it matter since I took team 2's rope and added it to team 1? Does that make a difference? Well, let's see. If I take team 1's force and I add it to team 2, clearly it doesn't matter because, and again, addition is commutative, right? So it doesn't matter how I add these. I'm still going to see that resultant force heading in this direction. So no numbers whatsoever to speak of, just the concept of the result of two forces can be found pictorially or graphically or with the diagram by adding these two vectors together, by copying and pasting one to the terminal point of the other like so, or taking this, copying it to the terminal point of that, and connecting the initial point to what we call the terminal point or the final terminal point there. Okay, so we're going to spend some time doing some problems with the numbers now and some calculations, but we're always going to rely on this to determine if we've done our calculations correctly and make sure that the answers we're getting actually make sense for the math involved.